I think I'm going to get started because it's 10:10. Hello, everyone. Welcome to the Warren Lecture today. It's my great pleasure to introduce to today's speaker, Professor Garrett McKay from Texas A&M University. Professor McKay received his undergrad and master's in chemistry from California State University and did a PhD in environmental engineering at CU Boulder. I'll try to get that right. And a postdoc training in Colorado School of Mines. And his research topic is broadly on chemical processes in natural engineered systems, particularly environmental photochemistry, optical and photophysical characterization of carbon-based chemicals, materials, nanostructures, and treatment of emerging contaminants, which you're going to see today on PFAS. I met Garrett the first time when we were both poster award winners in the Gordon conference, and we both have to prepare a 5-minute presentation overnight in a conference. So that was a bit nerve-wracking process, but we both made it through. And I remember that 5-minute talk, my impression was this very fundamental thinker and a really rigorous approach to research. So he has won many NSF funding, and including career award and early career award from Army Research Office. So I will give the stage to you, Garrett.
Thank you. Boy, thank you so much for the kind introduction. It's really great to have the opportunity to be here, and I'm just really grateful for the opportunity. So, as mentioned here, I'll be talking about our work on reductive defluorination of PFAS, but really the story is a photochemistry story. And I know many folks here know about photochemistry, but not everybody does. And so I'm going to take some time to go through the fundamentals and make sure we're all on the same page. But before that, I want to tell you a little bit about my adventures in Minneapolis. So I had the opportunity to arrive early and get to explore the city a little bit yesterday. And as I was looking, at the weather, of course, to see what it's going to be like, it's a lot colder than Texas. And so I had to dig out this vest somewhere in the closet. I hadn't used it for 6 months, and it's kept me warm throughout my time here. I used it yesterday morning to go on a run, and something I didn't know that y'all had is turkeys. Just wandering the city, right? So surprised to see them walking around people's front yard, and it's like, wait, what? These are huge, huge birds. And then of course, I had to carry this 5-pound book with me to go get a picture at the Stone Arch Bridge. And if any of you have been down here, I'm just lucky to still be alive, right? Like, it's not an easy place to get to. So it was a lot of fun, and a lot of fun to explore. So I haven't always lived in Texas. I haven't always been at Texas A&M. Like Boya mentioned, I grew up in California, and particularly in the Central Valley. So if you know anything about water issues, water distribution, California is kind of a hotbed for what not to do in that area. I got interested in environmental issues growing up there because there was a lot of agriculture, and we saw this groundwater subsidence, water quality issues, and so that prompted me to pursue an environmental science degree at California State University, Long Beach, and then I switched to chemistry at some point there. Of course, after graduation, I needed a job. I knew I was going to go to PhD school, but needed to stay in town for a year, and so I just took any job I can get, and thought, hey, I can do anything for a year, right? But the job I ended up getting was a quote-unquote science consultant for this law firm, and the law firm was actually representing the National Rifle Association, doing work on leaded ammunition, contamination, and I was wrong. I couldn't do it for more than 3 months because it wasn't very ethical. So I left to be an adjunct professor and got experience teaching for a year before going to the University of Colorado Boulder. And then I did a postdoc at the School of Mines for about 1.5 years. And if you haven't seen the mascot for the Colorado School of Mines, this is Blaster Burrow. And really, if you look up close, you can see he has a stick of dynamite in his mouth, which he's probably letting go before it explodes. So I have the great opportunity to lead a research group at Texas A&M. Kind of the core theme of our group is environmental photochemistry. And so we look at natural systems and engineered systems and try to apply fundamental models and understanding towards making advances in science and engineering. So, brings me to today's talk. This is a brief outline. So the first 2 bullet points are going to kind of get us all on the same page in fundamentals and introduce the topic of PFAS. And then in the last 3, the first is a project that we worked on for quite a long time, kind of developing this probe compound to measure aqueous electrons. And then the last 2 are some applications of this. So, what is environmental photochemistry and why is it important in our field? And it's important in both natural systems and in engineered systems. And so this graph shows the solar spectrum both before and after the Earth's atmosphere. And you can see there's a broad range of wavelengths. The wavelength range that we're interested in particularly is this UV invisible region because photons coming in at these energies have the equivalent energy to chemical bonds. And so from the energy balance perspective, there's the possibility to break those chemical bonds, whereas farther out here, you're just going to vibrate the molecules and there's not enough energy to do bond breaking. There can be different roles for light in natural systems. So the fate of organic contaminants. I know Professor Arnold isn't here, but he's done a lot of work on triclosan photolysis over the years. And then photons also convert organic carbon, organic nitrogen, sulfur to inorganic products, and this plays a role in global cycling of elements. Now, on the engineered side, we take advantage of these high energy photons in water treatment. So for processes like disinfection, treatment of emerging contaminants and oxidation processes. So we can use conventional sources like low pressure mercury lamps. And nowadays there's a lot of interest in LEDs as well, as they're making these at shorter and shorter wavelengths at higher powers. So again, Stone Arch Bridge. What are the main processes in environmental photochemistry that we need to consider? So one of these is direct photolysis. So in direct photolysis, a target compound absorbs light. It excites the electrons in that molecule to a higher energy state, Tc star. And then from that part, it goes on to form products with some efficiency. Indirect photolysis is when something that I'll call a sensitizer or sense absorbs light to form an excited electronic state, just like this. But then the excited state sensitizer either decomposes, interacts with other parts of the water matrix to form reactive transient species like hydroxyl radicals, excited states of oxygen, triplet excited states as well. And what these do is these interact with a target compound to form products. So it's an indirect way that the target compound gets degraded or transformed in the environment. If we want to think about the overall rate of these processes, we want to consider both. What is the contribution from direct photolysis and what is the contribution from indirect photolysis? So how did I get interested in this? I know that the invitation mentioned to talk a little bit about your journey, from the kind of the student perspective. And so I think this is, an important part of my story. So when I was an undergrad and master's student at Cal State Long Beach, my advisor, he collaborated a lot with the Orange County Water District. And they're a full-scale water reuse facility in Southern California. And what he was interested in was this part. How quickly do these transient reactive species react with different target compounds? And so the reason for this is that if you apply your kinetic models, the rate of target compound degradation in that system is a function of really 2 things, this reaction rate constant. And so in the case of OH, which is relevant for these UV advanced oxidation processes, we want to know what is this bimolecular rate constant for reaction of the hydroxyl radical with different target compounds. These tend to be very fast, 10 to the 8th to 10 to the 9 per molar per second. The other term is this OH radical concentration. And a simplified version of this is, what is the rate of OH formation in the system as light interacts with hydrogen peroxide, divided by all of the sinks. Where does OH go? Some of it reacts with the target compound, some of it reacts with other scavengers in the water, and so we need to know that. And typically these values are pretty low. And so in his lab, we measured rate constants for things like target contaminants and also scavengers of hydroxyl radical. Now, this was an atypical research experience because the best way to do these rate constant measurements is a technique called electron pulse radiolysis transient absorption spectroscopy. So we didn't have one of those sitting in the lab at our state university system in California. And so he put his research group on a plane every few months, and we traveled to Chicago Midway and then drove to the University of Notre Dame, where they have a radiation lab and this equipment. This is what the system looks like. There's more back here, but the basic idea is that it accelerates X-rays very, very fast into this cuvette filled with water. When that ionizing radiation interacts with the water molecules, it produces these transient radical species like OH, among others. And then you watch the kinetics directly using transient spectroscopy on the microsecond time scale. Of course, this is like really high energy radiation. There's a control room, and you walk through several leaded walls to get out of here, and you have to turn a key to make sure you don't get locked in, essentially. And so you can see this computer and chair right here. This is where I sat back in the day. I think this is proof I didn't believe in haircuts at one point in my life. But it was a lot of fun and kind of a different experience. Throughout my time there, I also did work in the lab at Cal State Long Beach, and that was an important part of my research too. Oh yeah, one last thing. So, right, I see Professor Lepar over here, Notre Dame. So, if you're a football fan, you know that the Notre Dame has this play like a champion today. Now, in the radiation room, kind of to the left of this computer, there's the first door that you walk through. There's this sign, "Irradiate like a champion today." So you saw this every time you went in, and it kind of reminded you, like, hey, don't get stuck in there. Do good work, measure correctly, do a good job. So, I share all this, partly for the students, but the kind of the takeaways and what guided me in starting my research group is partly from my master's, partly from my PhD. My advisors tended to want me to focus on measuring and understanding really the core parameters that govern a system, right? So don't just measure transformation rates of your target compound. What is the rate constant? What is the actual hydroxyl radical steady state? What is the quantum yield? All of these are fundamental parameters that govern the system. And so that's kind of what I've taken. The other is, presentations tend to be like the Instagram or social media version of a research group, right? So these are all the things that kind of ended up being successful. I'll share a little bit of what was not successful along the way, but just know that there's many things along the way that didn't work, and that's normal. Okay, so what are PFAS and why do we want to destroy them? It kind of dawned on me like a week ago that I was coming to Minnesota to talk about this research, but you all are pretty aware of the really significant impacts. Many decades ago, scientists discovered that the tanks they were using for perfluoroethylene for alternative refrigerants, they were going to let out the gas and nothing came out. The weight hadn't changed. So they cut open the tanks and discovered that the tetrafluoroethylene had polymerized into this PTFE, which ushered in eras of fluorine chemistry. So we're most familiar maybe with nonstick pans and use of Teflon there, but PFAS have been used in lots of other materials and over the last several decades. PFAS is a large group of compounds, thousands of compounds, but there's individual classes within that group. So some of the most commonly studied are these perfluorocarboxylic acids and perfluorosulfonic acids. So the per means that every CH bond on the structure has been replaced with a CF. And for the carboxylic acids, there's this head group that is a carboxylate, and the sulfonates have the sulfonate head group. Now, these charges tend to make them really soluble and more mobile in groundwater flows, and so there can be long-range transport of these compounds in water. It's a concern because there's lots of potential contamination sites. So this was from a pretty recent study in ES&T Letters that used proximities to military sites, major airports, wastewater outflows, and industrial facilities to estimate how many potential water sources are contaminated. And the number is very high. And with proposed MCLs coming at some point in the future, drinking water utilities will have to manage this. And a lot of these, some come from industrial sources, but another large source is aqueous film forming foams that are used to put out jet fuel fires. You can see a picture of this here, and these are really more for the major airports and military sites where they do these fire training exercises. Now, the problem is really two things, right? The compounds are very toxic at low levels, and they're also designed, to be really resistant. So there aren't significant natural attenuation mechanisms, and even in engineered treatment, there's no silver bullet destruction technology yet that will degrade these compounds and alleviate their toxicity. There are several destruction technologies that people have been looking at, and one of them is based on the generation of aqueous electrons. And so you might be thinking, well, what is an aqueous electron? There's several ways you can generate it. One of them is with ionizing radiation, back what we used at Notre Dame. Another of which our group has been focusing on is UV activation of different chemicals, like something as simple as sulfite, something as simple as iodide. When you shine light on it, it produces this aqueous electron. Again, you might be thinking, well, what does that mean? What is aqueous electron? So you can think about it as an electron surrounded or hydrated by water molecules. And it actually has a very prominent UV visible absorption spectrum with a peak at about 700 nanometers. And if we remember back in general chemistry, if you put sodium metal in water, what happens? It explodes, right? And so if you put sodium in liquid ammonia, it doesn't. And you can actually see the blue color coming from that electron off of sodium. And so it absorbs prominently at about 700 nanometers, and so the light that gets through is blue at around 450. Now, the basic idea here is that if you expose a PFAS to enough aqueous electron, that the CF bonds in PFAS could be degraded or reduced, chemically reduced to fluoride. And if we can quantitatively take all of the CF bonds and make them fluoride, we have essentially achieved our goal because fluoride is comparatively non-toxic. And so our approach is to think about generating this photochemically. We can do this in the lab. There's also full-scale technologies in water treatment used for photochemical processes. And so this is kind of our motivation and reason for pursuing this relative to others. Now, technological progression-wise, these are not at a full-scale treatment, right? If we think about the oxidation side, UV-ARPs are, but these are not. This is more still at the lab scale in some pilot studies. But it's important to think about, where might we put this in a UV-ARP treatment train? So most of our contaminated source waters, there's some exceptions, but nanogram per liter to microgram per liter levels is pretty typical. And so you're not most likely going to use a destructive technology directly there. What's being used in the field, if a water source has these issues, is either granular activated carbon or ion exchange. There's some applications for filtration technologies like nanofiltration and reverse osmosis. And that gives you a clean water, but then, eventually all of your absorption sites and GAC or ion exchange are used up. Or if you're using a filtration, the water that doesn't go through the filter has to go somewhere. And so that gets concentrated in PFAS. Now, all these things remove PFAS from water, but they do not break down the CF bond. And so on the these are going to generate a concentrated waste stream. That's going to be maybe milligrams per liter or grams per liter concentration in PFAS. And this is where you might consider putting a destructive technology, because relative to the amount of water that has been cleaned up with, say, activated carbon or ion exchange, you're treating a relatively low amount of water. So two last things. One is that, for activated carbon, thermal regeneration is kind of what's being considered there. So our regenerate here is, the way we're thinking, is actually coming from ion exchange, not GAC. And the other is that as you concentrate PFAS, you're also concentrating other things in the water, right? DOC, nitrate, alkalinity, like all these things. And so it becomes more important then, as your water quality gets worse, so to speak, that you understand how much aqueous electron is being formed and where is it going. How much is going to react with PFAS versus other stuff. And so this brings me to kind of our first study. When I became an assistant professor several years ago, was looking at this literature and thinking, this is really cool. Really, it seems like there's a lot of promise. This technology, people are getting some good results. But what was missing was this quantitative understanding. How much aqueous electron is being formed and where is it going? And partly the methods weren't available. Nobody had developed, what the photochemists in here know as probe compounds for characterizing these systems. And so that's what we set out to do. Before getting into that, I want to delve a little deeper into this, fundamental parameters here. So if we think about replacing TC with PFAS, there's really two things: this direct photolysis contribution. For most PFAS at 254 nanometers, direct photolysis is not occurring. At shorter wavelengths, perhaps with LEDs or different light sources like krypton chloride excimer lamps, they actually do undergo direct photolysis, and so that could be beneficial. On the indirect photolysis side, which is what I'm talking about today, there's two important parameters: this bimolecular rate constant. We don't have control over this. This is a constant with ionic strength and temperature. We can't do anything here, but we can control this aqueous electron concentration. And this depends further on two things: the formation rate and scavenging. And so the formation rate, you can think about, how much of light is getting into my solution, getting absorbed by the aqueous electron source, and eventually forming that species. The scavenging part tells you, once it's formed, where does it go? How fast does it react with water matrix components versus my target compound? And so we wanted to, set about to measuring this aqueous electron concentration using what's called a probe compound. And this, occupied several years of my PhD student in ours life, and I just kept telling him, keep trying, keep working on it, because once you get this method, it'll be worth it. Nobody has done this before in the system, and it could yield some good insights. He tried many things, many probe compounds that didn't work. This is a little bit about the experimental setup we were using. They're these immersion well photoreactors from Ace Glass. We used low pressure mercury lamps that emit at 254. Because of the high concentrations of PFAS expected in destructive technologies, we were spiking in about 1 milligram per liter concentrations into our system. And then we took aliquots out for analysis periodically and did spiking of mass labeled surrogates and kind of all the QA/QC stuff you would do for PFAS. And so after much effort, you could say, trying several probe compounds, he kept coming back and saying, well, we saw this in our selectivity test, and like, oh, well, that seems like it's not working. We eventually landed on chloroacetate, or MCAA for monochloroacetic acid. And the essential idea behind a probe compound is it gives you like a snapshot of the aqueous electron concentration at that point in time. You spike it in, monitor its kinetics for degradation or maybe the formation of some product, and it kind of gives you a sense of what the reactive species concentration is at that point in time. And so the reason that all the others failed is that they failed our selectivity tests, particularly where we took MCAA and spiked in a good amount of nitrate. For all the other probes that my student Ben tried, they just, there was still degradation when nitrate was added. And what that told us is there was some other reactive species being generated in the system that was not aqueous electron that was capable of degrading this probe. And so it wasn't selective enough. Ultimately, this is the one that worked, and it's the one that we went with. But there were a lot of ones before this that didn't work. So after we got this to work under deionized water conditions, Ben kind of had this idea to look in different source waters and ask the pretty simple question, does the initial source water quality impact the treatability of PFAS in this UV-ARP system? And these are all drinking, the Lake Bryan isn't, but BTU Aquifer, Ohio River, LWC, RBF, these are all drinking water sources. These two are from Central Texas, and you can see really high alkalinities. The Ohio River is from the Louisville Water Company, and they send their water through a riverbank filtration system, which removes a lot of the nitrate and DOC. Ben had worked as a consulting engineer in Kentucky for several years and knew these folks, so they were able to send us some samples. So we went about measuring the aqueous electron concentrations with chloroacetate in each of these source waters. And so there's not a super important detail for this talk, but we developed this RE minus UV. It's the Fluence normalized aqueous electron exposure. The advantage of this is it accounts for different light sources. So say you're using a medium pressure lamp versus a low pressure lamp or a different wattage or something like this. RE minus UV will account for that. And that was something we thought was valuable. The way that you can think about it is essentially akin to the aqueous electron concentration. So that's the way to think about it here. And what we saw is that RE minus UV in the source waters, it depended on this formation term, right? What is the rate of aqueous electron formation in the system? In these data, you can see that the degradation rate of chloroacetate increases with increasing concentrations of sulfite. And that's true for all of our source waters. And this makes sense because as we add more and more sulfite in, more of the photons coming into the system get absorbed by sulfite and less get absorbed by the background water. And you can see that for ultra-pure water versus our water samples, there tends to be a pretty good correlation between the absorbance of the background water at 254 and the RE minus UV. Where it breaks down, though, is this Ohio River sample, right? So what's going on? I didn't do that. Hold on. Whoa, 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 whoa. Hold on. That was scary. I don't know what happened. Okay. So what happened? So what was happening actually is that this Ohio River sample had a good amount of nitrate. And so what we did is, from this RE minus UV parameter, we can also calculate the scavenging part. And we said that's another part of this story. Where is the electron going? And it turns out for this Ohio River, it's very fast. So for the measured ones, this is coming from the probe, and the bars represent our calculated value. And you might ask, well, if you have a calculated value, why do you need a measured value? You're not always going to know all the water chemistry parameters, and there might be some important scavengers that you can't measure. And so, historically in the photochem literature, we also, we want to measure scavenging capacity. The take home is that for Ohio River, it's much larger than all of the others. So that explains the deviation in RE minus UV at increasing sulfite concentrations. All right, returning to our original question. How does the aqueous electron concentration at time 0 impact PFOS degradation over a 24-hour UV sulfite experiment? Well, PFOS at 8, 12, and 24 hours for Ohio River is lower, and the defluorination, which represents that ultimate conversion to fluoride, that's kind of our end goal in the process, it's higher. That's unexpected. That was really surprising to us because this RE minus UV was lowest. Outside of the ultra pure water, which clearly showed the best performance, this would be expected to be the worst. And so we thought, okay, well, what's going on here? And all of these values were taken at the experiment time 0. Then turned on the lamps, spiked in MCAA, took the kinetics for MCAA, the end. And so what he thought to do was, instead of just doing that initial point, was, let's measure it over several hours, the entire 24-hour experiment. And this is something that I don't think we do a lot in photochemistry, and is maybe a novel contribution of our study, is characterizing the time dependence of reactive species concentration in our system. And so what he figured out is that, over half an hour to an hour to 7 hours, the degradation rate of our probe increased up to a certain point. And the probe was gone by the time we added our next spike, right? So it's not as if MCA was just accumulating in the system. We spiked it in, it degraded. We spiked it in later, and it started off at the same initial concentration. When we look at RE minus UV, going from 0 hours, it's initially very low, but up until the maximum, it's over a 13-fold increase. And so what this is saying is that the aqueous electron concentration in the system is changing quite a bit over this treatment process. Initially, it starts off very low and then gets higher and sort of levels off. What about the other samples? What does this have to say? Well, ultra-pure water, that makes sense. That one's the highest. Ohio River and LWC RBF, those are the next highest. And overall, the lowest ones are the samples that have this one had high DOC and high alkalinity, and then the BTU aquifer had high alkalinity. And this was a little bit unexpected because, if you look at this, it's a pretty benign groundwater, right? Low DOC, just little absorbance at 254, but overall that had the worst performance. Another key, look at the inset, 0 to 2 hours. The trend is swapped, right? The green one and the blue one, especially the green one is higher, whereas at the end here it's not. So the other part of this is the scavenging capacity. So this shows the measured scavenging capacity as a function of time. The take home here is that the ones with high alkalinity tend to be higher around this 0 to 4 hours, about 4 hours onwards, whereas at the very, very beginning, less than half an hour, this Ohio River with a lot of nitrate is the main, has the highest scavenging capacity. So we were surprised by the alkalinity results. So Ben did a pretty simple test where he spiked in, and instead of just using ultra-pure water, he used 10 millimolar bicarbonate as a background. And lo and behold, what we see is that RE minus UV remains low, and the defluorination in that experiment matches what we see in the low alkalinity samples. The scavenging capacity also remains pretty high. And so what we ended up sort of discovering was that this is like the kind of tortoise and the hare analogy, parable. If you've ever heard this story, it goes something like the tortoise and the hare were agreed to do a race, and the hare is really fast, so he runs, and then eventually he's like, oh, I'm going to win this race. I'm just going to stop and take a nap. And then the tortoise is like, I'm just going to go really, really slow. And eventually the tortoise passes the hare and wins. Maybe an analogy to completing your PhD, right? Just keep going, slow and steady. But the way that we were thinking about it is like this, that the hare is like nitrate. Nitrate has a really fast reactivity with aqueous electron. And our results show that nitrate and nitrite are degraded after the first 30 minutes in this Ohio River sample. What that leaves in the other ones is carbonate species. And we initially did not expect carbonate species to be important because overall they have a pretty low reactivity with aqueous electron. But it seems like after we've degraded most of the main electron scavengers, they can actually play an important role. So the other part of this was electron scavenging by DOM. And so this is sort of a new field, right? This UV advanced reduction process. And DOM is likely to be one of the important scavengers. Nobody had investigated this. Furthermore, when we look back at our scavenging capacity data, this Lake Bryan sample that had the highest DOC tended to have the largest long-term scavenging capacity. And so this was a really nice opportunity to call up my master's thesis advisor and say, hey, can we come on a plane to go back to the University of Notre Dame? You just haven't got enough of the Fighting Irish, right, to go and to go back. And so that's what we did. We used well-characterized DOM isolates. So this is Steve, and we went back and did these pulse radiolysis experiments. So the other key here is that in this ionizing radiation, it does produce a known amount of aqueous electron. And so we can spike in tertiary butanol, which scavenges out the hydroxyl radical, and then we can actually see directly with the transient absorption spectroscopy the aqueous electron signal. We were trying to get some structural information, what factors of the NOM control its reactivity with aqueous electrons. So we used 8 different DOM isolates. Some of them we looked at 3 pHs and temperatures and different ionic strengths as well. A little bit about how this works. So we kind of set up this competition reaction where aqueous electron is formed. It can react with DOM or other scavengers in the system. As we increase the concentration of DOM, the parent rate of aqueous electron increases. So this is monitoring its absorbance directly. The kinetics get faster, and we can transform this into a pseudo first order plot where the slope is equal to the bimolecular rate constant. And so the take home here is that the scavenging constant for aqueous electron by DOM is about 1.8 times 10 to the 4 liter per milligram carbon per second. And if we had to take a guess, we might say it's somewhere around here, but at least we now have an accurate value. And if you're interested in knowing its contribution to the overall scavenging, you would multiply by this DOC. Now we got this from an average of all the values here, and these are for our different isolates. We didn't see any structural dependence. So this was one of those things that didn't work, right? We were thinking maybe it would correlate to aromaticity or molecular size or charge density or something like that, but it didn't work out that way. But having this rate constant now allows us to compare the scavenging of DOM relative to other things. And so it's a little bit complicated graph to show this, but on this y-axis, that's the scavenging capacity. Again, where is the aqueous electron going? The lines here show different CtCO3s. This is from a different paper, not by my group. And ultimately, at a really high CtCO3, say 10 millimolar, the scavenging capacity of DOC can approach the level from these carbonate species. And another one on here is nitrate. You can see oxygen at 0.1 ppm is a lot lower. And this H plus represents, I think, pH 9. And so what this is telling you is that at 10 milligram carbon DOC per liter, like very high for a source water, but still reasonable, it's less important. But at 100 milligram carbon per liter, the kind of situation you'd expect in a concentrated reject stream, DOC is going to be an important scavenger of aqueous electrons. So this figure kind of summarizes our current thoughts on this. In our experiments, in the first 0 to 2 hours, nitrate and nitrite are the main electron scavengers, and DOC shields sulfite from absorbing incoming photons. Between 2 and 4 hours, DOC and carbonate species are the main electron sinks, and after 4 hours, carbonate species are the most important. So the last few minutes here, I'll talk about our efforts to apply what we've learned from this probe compound and from our studies of DOM to treatment of PFAS in a membrane concentrate. So we had the opportunity to work with the Orange County Water District, and when we took some of their ROC from their water reuse facility, it wasn't enriched in PFAS, but we thought this is going to be a good test bed to try some of these ideas. And it's authentic ROC, and it has pretty poor water quality. So what do we do? The first thing we did was kind of combine some of their historic data with our own measurements to compile their water quality. And the take home is that it's high DOC, high absorbance at 254, tons of nitrate, lots of alkalinity. It's not looking good, right? All the things we said wouldn't work well or would be difficult are present here. Another one that was difficult is in all the prior experiments I showed you, we used pH 9.5. And that's because, that's driven by the speciation of sulfite to bisulfite, actually. But other research groups have shown that in this UV sulfite system, if you use pH 12 versus pH 10, it gets a lot better. But of course, in something like this, you have precipitation of calcium and magnesium. And so Ben had to do a simple cation exchange process to get rid of these, and then we could use pH 12. In the initial experiment he did in this ROC, we expanded our PFAS suite to short chain compounds as well as perfluorocarboxylic acids. And what he saw is that using this optimized, from the literature, pH 12 system just didn't work very well. Over 48 hours, there was, maybe 70% defluorination, and only PFOA and PFBA degraded below our detection limits after 48 hours. So not looking too good. So as a first step towards addressing this, we thought, well, let's tackle DOC. Can we get rid of the light absorption from DOC and maybe remove some of its scavenging capacity? So we used a pre-oxidation step with UV persulfate. And after a shorter amount of irradiation time, a lot of the absorbance by DOC is removed during this oxidation. And when we measure RE minus UV, we can see that it also is much higher. So the purple line is the base level conditions, pH 12. The orange line represents with our pre-oxidation. And what we noticed is that after about 12 hours, the sulfite concentration really started going down. And so in a subsequent experiment, Ben did additional spikes of sulfite to maintain a higher level. And in this system, we are below our detection limits, for PFAS, and these aren't like PPT levels. So just keep in mind, we started off with 1 milligram per liter for each compound, and use a certain amount for SPE. So it's not like we've solved that complete problem, but in the it's much lower than we started with. And the other thing is that we get pretty close to 100% defluorination. The compound that's still stubborn is PFBS, the C4 sulfonate. But ultimately, it doesn't get us all the way to DI water conditions. This graph shows the degradation kinetics we measured for PFOA and PFOS at pH 10 versus pH 12. And so it doesn't get us all the way there, but it is a step in that direction, right? If we can get to our optimized conditions in DI water somehow, that would be really great. It doesn't get us all the way there, but it is a step in the right direction. And where we're focusing now is actually this first 4 hours. You kind of notice there is some noise in the data, but actually 8 hours. Within the first 8 hours, there's not really any attenuation. And I think this is coming probably from the high nitrate levels. And so that's kind of what we're tackling now. How can we deal with nitrate in a way that optimizes, or how quickly the aqueous electron can be getting to the PFAS and degrade it. All right, so some of the take-home messages from this talk are, one, the chloroacetate and the RE minus UV method provided a quantitative framework for evaluating these UV advanced reduction processes. It was kind of frustrating to look in the literature, getting for research ideas, and one study said we degraded PFAS the quickest, but they were using an 800-watt lamp. Another one was using a 12-watt lamp and different concentrations of these electron sources and all that. And so I think having this standard approach is going to be valuable. Another thing there is that we see this really extreme time dependence in the aqueous electron concentration over this time scale. And what that's making me think about is other photochemical processes, like UV-AOPs certainly have less fluence than we do here, but I'm kind of wondering how much our scavenging capacity and other photochemical parameters change in those. Both the tortoise and the hare are important in scavenging electron away from PFAS. And so this, we need to think about the role of bicarbonate. The kind of the short story there is that actually at pH 10, H2CO3 star, true carbonic acid and dissolved CO2 can play an important role in scavenging away aqueous electron, even at pH 10, where that's a pretty minor species. And so I think that's why pH 12 performs so much better than 10, but it's something we need to think about. Targeting DOC increased the treatability of PFAS when we spiked it into the ROC, and so that was one step of the puzzle. The other is tackling, how do we get rid of nitrate faster? PFBS is still stubborn, and it's not for just UV-ARP, it's for other degradation technologies as well, and so we haven't completely solved that either. So with that, I'd like to acknowledge, and thank all the folks who did this. Primarily Dr. Benjamin Fennell. He graduated with his PhD at Texas A&M this summer, and then we've had some undergraduate students working on this project. Adam, he graduated. That's why we're holding him. Shani Chavez, she worked with me as an undergrad and is now a master's student in the group. New postdoc, Angela Jung, and then collaborators. This grant was funded by NSF, the Texas Hazardous Waste Research Center, and you've had lots of fun along the way, and it's great to share that with you here. So thanks for your time. I'd be happy to answer questions.
Yes.
Nice talk, thanks. I wondered what's going on chemically that PFBS didn't degrade at all, whereas PFBA degraded really quickly, and PFOS and PFOA degraded really fast. So it doesn't seem like it's a sulfonate thing. So what's going on chemically that compound is sticking around?
Yeah, that's a really good question. So in general, perfluorocarboxylic acids tend to have, that's my timer to stop. Perfluorocarboxylic acids degrade much faster in general across the board. And actually, so I'll shout out to my colleague at University of California, Riverside, Jin-Young Liu. He's done a lot of really, really good work in this, and they've showed this systematic chain length dependence for perfluorosulfonates, but not PFCAs. So what they're thinking is actually that there's differences in the bond dissociation energies, or basically the energy of initial electron attack, that are influenced more by the sulfonate group. So if you do some of the computational chemistry on the system, perfluorocarboxylic acids, the energy of addition of aqueous electron doesn't depend on chain length. But for perfluorosulfonates, there's a really extreme dependence on the ease of access of PFBS versus PFOS. And so that's my understanding of what's going on there.
Did you try PFHXS?
We didn't in this study because we kind of figured, PFBS is one extreme for those, PFOS is the other extreme. But in some of my postdoc work and others, we've looked at PFHXS. And actually in this system, HXS does go along at a pretty decent clip. Compared to PFBS. So I'd say HXS is more amenable, especially at pH 12 relative to pH 10. So that is that is good.
Yeah, it's interesting it falls off.
Yes.
Thank you.
Yeah, thanks for the question.
So the for the chain length dependent for sulfonate, the shorter chain, it is harder to do the shorter chains.
Yes, and that is also true for other destruction technologies as well.
Hey, Garrett, I was wondering about the lack of a structural dependence for the natural organic matter. I mean, can you elaborate a little bit more on that? I mean, just carbon is carbon? Is that sort of organic carbon is organic carbon? Or?
Well, organic carbon isn't just, we can't all treat it the same, right? But it was, a little bit puzzling. We looked at a lot of things like, we're thinking electron accepting capacity would be, that might be a parameter. And so, it's kind of the thing that folks have done with NOM, which is, try to correlate to some bulk or maybe other, more specific physicochemical properties. And we tried aromaticity, lots of things. And really the only one that had a statistically meaningful correlation actually was the carbonyl content by NMR. And that actually makes sense because carbonyls are good electrophiles, and so it was not it was statistically meaningful, but causation-wise, yeah.
Have you dabbled with any synthetic NOM compounds or, with different structures to kind of test that out?
No, our framework, and I didn't have as much time to talk about it, was using smaller model compounds and saying like, if you take these 200 bimolecular rate constants and kind of group them by functional group, aromatic compounds that contain a benzene ring tend to be like over here. Compounds that contain a carbonyl group are way over here. If you just have aliphatic carbon and maybe nitrogen, amine or alcohol, it's way over here on the slow end. And so that's kind of guided our thought process. But the other thing, if I can, that I didn't show here again, is what's really interesting is that as you expose the aqueous electron, DOM, to the aqueous electron, the reactivity changes. So the values we measured were like T0 before in the NOM in its native state. But you can imagine as you expose it to these reducing conditions, you're changing its reactivity. And so Ben did an experiment with the probe compound that demonstrated it. And after a few hours, you lose all of the color, but the DOC in the system is still the same. So you're forming some small reduced, non-absorbing compounds. That have lower reactivity over time.
Great talk, Garrett. My question is related with the PFAS are usually in wastewater, effluents, wastewater, raw wastewater. So do you mimic any condition, like for example, synthetic wastewater and trying to run different isolated disordered matter present that to see how it's going to be that kind of reactions?
Yeah, so did we try to do any experiments in synthetic wastewater? We didn't target municipal treated wastewater directly, but the ROC is almost like so in the water reuse facility, they're taking secondary treated wastewater from all over Orange County, and by the time we get it, the water has gone through, I think, ultrafiltration, a few filtration steps, and by the time we get it, it's it's hit the ROC, and we get the reject from that. So, we haven't tried wastewater effluent directly.
Thank you so much for the amazing talk. So I had a question regarding the production of the aqueous electrons and how you quantify it. So it is being produced from some kind of sulfate species. It's sulfate and sulfite from what I understood. And you're probing the amount of aqueous electrons using a probe chemical. So if it's being produced from the source, what's happening to the sulfates and sulfites after it's being produced, and why are we not trying to trace the sulfates and sulfites, how it's degrading, as opposed to just using a probe?
Yeah, that's a really great question. So on the formation side, sulfite is serving as the electron source, right? So when you irradiate sulfite, it photoionizes to produce that aqueous electron, and sulfate is one of the end products of that series of reactions, right? And so sulfate, is you can quantify it with IC, and we see it in our peaks, but it tends to be a pretty broad. We didn't optimize, measuring sulfate, and that only gives you the formation side, right? That wouldn't tell you the scavenging side, essentially, and so. If you are using this in the future, recognize there are other electron sources that could be used, but sulfite is one of the most considered because the end product is sulfate, which is not great, but it's less worrisome than some of the other electron sources that are being considered, like iodide or organics or something like that.
So. This leads to the other question. So these aqueous electron species has relatively low time spans, very fast reactivity.
Yes.
So by the time you are probing it, do you think there are significant changes happening to the concentration? Because I think probing it, then measuring it, the whole process takes some time. compared to
Yeah.
that?
Yeah, so what happens is we spike in the MCA into the solution, and so it's a homogeneous solution, and so electron formed in that system has the opportunity to react with one of several things and decay by different mechanisms. One of those is reacting with chloroacetate. So the probe is spiked simultaneously to the time electron is being formed. And so it's almost like, you can imagine it like sitting like a fly on the wall, right? And it's just sort of observing everything that's going on in the ideal sense. So it's picking up on the solution conditions.
The chloroacetate how was that measured? It was probably a
Yeah,
fast method.
we used ion chromatography. So we withdrew samples, periodically and measured it with ion chromatography.
There
And
was a quenching before that was measured.
was there quenching? So we did dark experiments with sulfide and chloroacetate and didn't see significant quenching over the time scale. So.
Yeah, I just had a question about your methods for measuring the defluorination and the PFAS concentrations. With that percent defluorination, is that like a measure of the fluoride? And then when you showed the change in concentration of the PFAS, is that a reflection of any sort of loss of a fluorine, or is it a reflection of complete loss of all the fluorines?
Yeah, it's a good question. So the PFAS, CT over C naught, that's coming from targeted quantitation of the parent compound, and the defluorination is coming from fluoride measurement. So what we do is we take the molar concentration of measured fluoride and divide that by the calculated concentration of fluorine based on the initial concentration of the PFAS that we have in the system and the stoichiometry of fluorine to PFAS. Yeah, so it's kind of your good measure for ultimate destruction. There's a lot of intermediates that could be formed, and that's a concern. And so, but if we can track fluoride and get to close to 100% quantitation, we've dealt with most of the problem. But we can't say there aren't any trace intermediates in there.
Going off of that, I'm curious if you looked at all at the composition of the brine that you get after this process. Presumably it's really rich in salts, especially fluorides, and also small organic molecules, maybe some still fluorinated. And yeah, I'm curious if you looked at what the composition is, and also if you thought about maybe any ways to do resource recovery from that product.
We haven't thought about resource recovery from the product. That is not my wheelhouse, so maybe a collaborator one day in the future. But we have thought about the changing water quality, essentially. There are a lot of salts, but over time, when we do the pre-oxidation step, the DOC is lowered quite a bit, actually, and then the color gets better and nitrate is removed. So. The initial ROC does look different than when we started. Kind of where we're going with that is more so thinking on the ion exchange system. So right now we're working on taking PFAS laden ion exchange and desorbing with alcohol, base, and water, and then taking that really concentrated mixture and trying to apply the UV sulfite system to that.
Thanks.
Thank you.
Hey, thanks so much for the talk. I just have a quick question about, so you get the defluorination process to occur, right, on the PFAS. What do you do with the fluoride ion once it's off of the PFAS? And how do you safely get rid of it?
How would you safely get rid of it? I'm not 100% sure, if you were doing this, because there are destruction technologies out there being piloted, and some they're going to need to start being used a lot more as all these DoD sites get cleaned up. I imagine you'd have to, the ultimate goal is that your waste doesn't go into a hazardous waste landfill, right? You could somehow discharge, but whether that's achievable with any of these, I'm not 100% sure. I think, if you needed to meet discharge for fluoride, you could just dilute with some other water prior to discharge. But then again, you're having to worry about total organic fluorine. The methods for that aren't as, low detection limit as individual PFAS, so that's a challenge too.
Thanks.
Just fluoride ions maybe in toothpaste.
Yeah, we're not using it in toothpaste. I don't think so. Yeah, don't want to do that.
Other questions? I think I have a question maybe for my own learning and maybe for some students in my group and Bill's group is can you describe a little bit of the process you selected the probe compound? Because I think we're just, at least when I looked at it, I just looked at who has used this probe compound that worked. I just continue to use it. So what is the process that you and your student went through selecting that compound?
Yeah, this was the process right here. So we, we're trying several other probes because we wanted a lower detection limit than we could get by IC. So we're thinking something with HPLC would be great, like have an aromatic that you could see with UV-vis or fluorescence, but that didn't end up working out. So it needed to be selective. So kind of the thing you want is you want it to be selective under your conditions for that reactive transient as best as you can. And so all the other probes that we tried, this experiment with sulfite and nitrate, there was always appreciable attenuation of the probe. So it didn't work, yeah.
Thank you.
These are the experiments you would typically try. So like a dark experiment, a direct photolysis experiment, and then a quencher experiment. Those are the normal ones.
So these amount reduction, when you had nitrate, still considered?
Yeah, exactly.
Pretty.
Yeah, if we saw attenuation, when nitrate was present, we thought, well, something else is going on, whether it's a sulfite radical or something else. Yeah.
All right, let's thank our speaker again.
Yeah. Thank you so much.
Thank you.
Thank you.